Hi, this is Mrs. Villette, and in this video I'm going to show you how to take derivatives of functions that don't quite meet our categorizations for an exponential function or a power function. So in this example we have the function f of x equals x to the 4x. And just to understand why we can't use the power rule or the derivative of an exponential function for this, we have to review each type of function. So a power function is going to be of the form x to a power n, where x is the variable and n is a constant. Whereas an exponential function is of the form a constant to the power x. And so the variable is in the exponent and the constant is the base. So each one of those we have rules for taking the derivative of. So if I take the derivative with respect to x of x to the n versus the derivative with respect to x of a to the x, the derivative of x to the n is n times x to the n subtract 1. And the derivative of a to the x is the natural log of a multiplied by a to the x. So, in order to be a power function, the function has to have the variable in the base, and it needs to be raised to a constant. In order to be an exponential function, it needs to be a constant raised to a variable. This function is neither. There is an x in the base, which would make you think, hey, maybe it's a power function. But then the exponent is not a constant. And the fact that the exponent has an exponent in it might make you think it's an exponential. But in order to be an exponential function, I would have to have a constant in the base. So this is sort of a hybrid of a power function and exponential function, but it doesn't neatly fit into either one of those rules. So the way we're going to take the derivative is we are going to do what's called logarithmic differentiation. In order to take logarithmic differentiation, the first step is we're going to get rid of the function notation and we're just going to use y. So we're going to rewrite this as y equals x to the 4 to the x. The next thing we're going to do is take the natural logarithm of both sides. Now this is a move that we can do as long as the inputs and outputs to this function are positive. So we cannot take the logarithm of a negative number. So this particular function, we're not entirely sure that that's true, but we'll take a look at the graph later. So x to the power 4x, if x is negative, we're probably going to have some issues raising it to the x power, but we'll take a look at that and see what happens. Right now, let's just assume this is something we can do. So we can take the natural logarithm of both sides. Okay. Well, what that allows us to do is use the logarithm rule that says we can bring exponents down in front of the logarithm as a coefficient. So now I have the natural log of y equals 4x multiplied by the natural log of x. My goal is to find the derivative, so my goal is to find y prime. If I want to find y prime, then I need to take the derivative with respect to x of both sides. So you may recognize that in order to take the derivative with respect to x of this left-hand side, I'm going to need to use logarithmic differentiation. In order to take the derivative with respect to x of the right side, I will need the product rule. So on the left-hand side, the answer is 1 over y multiplied by y prime. We're taking the derivative of the outside, which is the natural log function, at the inside, 1 over y, and then we're multiplying by the derivative of the inside, which is y prime. On the right-hand side, I'll do the product rule. So I'll keep the first, I will take the derivative of the second, then I will take the derivative of the first function, which is just 4, and multiply by the second function. Notice here that the factor of x cancels, so I can cancel, and I can further factor a 4 out of everything. And I'm just factoring out of the right-hand side, in order to solve for y prime, I would need to multiply both sides by y. So now I've got my y prime isolated. My last step is to go back and substitute what y was. So I actually know what my y is. I've got the value of y back up here at my original step of defining the function. So I'm going to back substitute that in. So y prime is 4 times 1 plus the natural log of x multiplied by x to the power 4x. So that is my derivative. Let's go ahead and take a look at the graph and see if that derivative seems reasonable. Okay, so let's take a look at the graph here. So the graph of the original function is the red function. And the interesting thing is if you look at this on the Desmos app, you only get things to the right of the y-axis. But if you look at the computer, you actually get some other values. So I don't see any reason why this original function x couldn't be -1. Let's just try it and see what happens. So if x is -1, y would be -1 to the -4, which is the same thing as 1 over -1 to the 4th, which is just 1. So there should be a point over here at -1, 1. There should also be a whole bunch of other points, but the Desmos app just doesn't graph them for some reason. So if you look at this on a computer, you're going to see a different picture. But let's just go ahead and look at the information that we do have. So the information that I do have, I have my original function here in red, and then I have the derivative that we came up with by logarithmic differentiation in blue. I can see right here that my function is decreasing and my derivative is negative. So that makes sense. And in fact, if I kind of look at what's happening near x equals 0, it looks like my slope is approaching negative infinity, and my derivative is approaching negative infinity as well. Okay, right here, my function is increasing, my derivative is positive. On my original function where I have this appearance of a local minimum where the slope is 0, I have an x-intercept on the derivative. So all of that part seems to make sense. I encourage you to go ahead and look at your at this function on Desmos. Now, one of the limitations that I can see is even though the original function has more values for which it's defined, the derivative function clearly has a domain that is from 0 to infinity, because I cannot take the logarithm of a negative. So even though the function might have these other values in other places, it kind of does something like this, and it has some other pieces going like this. The derivative only works to the right of 0, and that's because we took the logarithm of both sides, and in order to do that, we had sort of made the assumption that the outputs and inputs were both positive. Let's take one more look at the derivative function, and I just want to show you that it's really interesting how this comes together and how it sort of looks like an exponential function and also looks like a power function. Okay, so our original function is x to the 4x, and then here's my derivative. If I expand this derivative out, I would have 4x to the 4x plus 4x to the 4x natural log of x. I'm going to simplify this first term in kind of a weird way. I'm going to take a factor of x out of the x to the 4x, and I'm going to put it in front of the function. So if you look at this, if I were to put these back together, this would be an x to the first, and if I added the exponents, I'd be back to the original thing. Okay, then I'm going to rewrite the second factor as natural log of x times x to the 4x multiplied by 4. Now, each one of these factors sort of looks like the appropriate rule for either a power rule or the derivative of a logarithmic function. Not a logarithmic function, an exponential function. So this sort of looks like a power rule where I'm treating it as if this 4x was a constant. So if I were to treat it as a constant and then I were to take the derivative, then what I would do is I would bring the 4x down. I would keep the base the same. And then I would subtract 1 from the exponent. So I'm treating the x like it's variable and I'm treating the exponent like it's constant. Okay, this other piece sort of looks like a derivative of an exponential. So I'm thinking of when I see this x to the 4x, I'm treating this x as a constant. And so I'm taking the derivative of the outside. When I do the derivative of the outside, remember I take the natural logarithm of the base. Then I multiply that by the exponential function. But then this is an exponential function with a chain rule, so I'd need to multiply by the derivative of 4x, which is 4. So this is not a technique that you should use to do logarithmic differentiation. Just do what it says, take the logarithm of both sides, and then implicitly differentiate. But it is kind of neat, and it pretty much always works out this way. When you have a function raised to another function, the answer that you get will be the sum of two separate functions. One of them that looks like you did the power rule and kind of ignored the fact that it wasn't really a power function. And then one of them that looks like you did it as an exponential function and ignored the fact that your base wasn't really constant, but you treated it as if it were constant. So I know that's a little bit of a long video, but hopefully you understand the idea of how logarithmic differentiation works. And then also one of its limitations is that you have to assume that that output function is positive, otherwise it does not work.